Hello and welcome. We are going to be talking today about Lesson 17. We are in ECE 252 and our topic for today is trees. So far we've seen a number of different types of containers. Something like the bag is very unordered. Arrays themselves are actually data structures and they are very ordered. There's a certain particular index for every single piece of data. And we've got things like lists that are chained together. Also, things like stacks and queues, you can put things in, but you can't specify what you take out. So there's many different arrangements for data structures, but today we'll talk about one that's arranged in a nonlinear fashion, but one that you probably use every day in your thinking and is a great way to organize certain types of information. So when we talk about trees here, one of the things I'd like to begin with is thinking about drawing a tree, the kind of plant a tree. So if you were to draw a tree in a cartoon fashion, you might draw a tree like that, or if it's a coniferous tree, you might draw something with little things coming off. I just wanted to tell you that when I was in second grade, my art teacher showed me the way to draw a cooler tree. So you start with the trunk, and of course here you've got the roots in the ground, but we don't always draw those. And instead of just drawing a cloud around it, we draw the structure of the tree. And so at each point, you make a little V. And at each of those points, you make a little V. And at each of those points, you draw a V till they start getting into sticks. And in a recursive fashion, we just branch off all those trees until we get down to the base case, which is I'm tired of drawing little sticks. But you can see this kind of forms a tree, and then after that I guess we were supposed to just draw our leaves around it like that. But this idea here, where you have a branch and then two more pathways, and then those pathways turn into two more pathways and so forth, is this idea of a tree, and we call these branches in the tree, but we also call the act of going in two different ways branching. Okay, so with this in mind, when we talk about a tree in computer science, what we mean is something that's going to be flipped on its head. We're going to draw it differently. And you've probably seen this, so this would be an example of a tree, where you have some root node, like with the roots here, and then they branch down, and then they move through. This is the idea, the abstract data type of a tree, where you have nodes that have connections to other nodes, that have connections to other nodes. However, we impose the restriction that there's kind of like this downward flow of connections. So things flow downward, and they expand as they get farther and farther down. But remember, this is kind of upside down in a tree, whereas this is the root, and then the branches are going down. Well, in nature, we would say that a tree goes up. In any case, it's going to be representing information like this. So what can we do with trees? What sort of information can we develop for trees? Well, you can imagine a work list. So let's say that we wanted to build a house. So we want to build a house, and there's lots of tasks associated with building a house. So we could then break this down into a number of different things. For example, we might need the foundation. The foundation, and then the walls. The walls, and then we would need the roof. There's lots more to a real house than that, but let's say that we would break it down. And we want to organize and schedule all the subcontractors and the workers. So we have to understand that these things, certain things have to be done before one another. As a matter of fact, you always have to have the foundation done before you can build the walls, which also means then that the roof has to wait for the walls, which has to wait for the foundation. But we don't want to just say foundation as far as our work breakdown. We would want to be able to schedule that into smaller and smaller chunks. So maybe you've got to have the excavators come in, and you've got to handle the dirt. And then you might need to pour concrete. So we've got the foundation, dirt and concrete. There'd be some other things in here, putting in rebar and so forth. But this is the idea that you have to do the foundation. And in order to get the foundation done, you have to do all of these subtasks. And if you were organizing a schedule with a big work crew, maybe you would break this farther and farther down about what worker 1 has to do, what worker 2 has to do, what worker 3 has to do, and so forth. Now with the walls, you've got to have the studs. And then also in the wall, we've got the electrical. So we've got the electrical, and then then maybe we've got to paint them. So of course you have to put up the studs before you put in the electrical, and then be drywall here, I guess. But then you'd have to do the paint. So there's a dependence, but the walls themselves depend on all of these jobs being done, in this case 3. So with roof, you can imagine that you'd have more and more things. But this is an idea of a tree, and it's a very natural way to think about task completion. So this would be an idea of a workflow tree. Another tree that you've probably seen before is you think about a family tree. And so if you have Josephine Will and then Robert Lincoln Will, they usually do this with a dashed line. And then they have several children. And so that's, let's see, there's Bobby. And then there's Jim. That was my dad. And so then Jim, he had, and then you'd have a little dash line with Galen here. But then you have Mike, you have Steve, and then you have Jeff. So we've got all of these. They break down. That'd be a family tree. And notice if you were to have a family tree data structure, you'd have to bake in this idea of marriages and divorces and remarriages and so forth. So family trees in reality end up being rather complicated to be able to program all the relationships, but still the underlying concept is that you have a tree with information flowing down. What else would we have? Well, certainly an org chart. We call it an org chart, but an org chart is actually a tree. So you have something like the CEO, and then you've got your VPs. And then you've got your directors. And there may be 3 directors reporting to VP2, only 2 to VP1. Maybe VP3 has a pretty big crew, and so they've got 5 people reporting to them. So this is the idea here as far as an application that would use a tree. Okay? So these are very useful. Now, when we look at these 3 examples, we think to ourselves, what are we going to have to store? How are we going to have to relate these things to one another? So you can think to yourself, well, the CEO would have to have 3 different nodes. So we're going to have an object for the CEO, an object for VP1, VP2, VP3. So whatever information we would want to contain inside of this would have to be a part of our class. That would be the member variables. And the member data that it would have would maybe give the name, the employee number, how long they've worked, their salary. There'd be a lot of information contained within that node. But the tricky part is that this node then has to know about its children. So we would have to represent a way of keeping track of all of these edges. Now, normally with the tree, we don't put the arrows in because the implication is that the information is really going down. But if we want to think about what we've been referring to as pointers, the CEO is going to have to store 3 different pointers to employee objects, whatever we would call the employee nodes. But then it's going to have to keep track of these 3 nodes. Then notice VP1, it only has to keep track of 2 nodes. And VP2, we'd have to keep track of 3. VP3, well, they're going to have to keep track of 5 nodes. And unless there's a hard restriction on your tree, in general, any parent can have any number of children unless there's an external constraint on it. So we would have to be able to have a node that has a collection of pointers and an arbitrarily long set of these. So it really doesn't work in order to have discrete variables for a general tree like this. So if you had a bunch of discrete variables, you'd have to say, well, what's the biggest number of people reporting to any given employee? Okay, well, we'll go with that and we'll make discrete variables. Well, that doesn't end up being all that great. You might want to think, well, instead of just using discrete variables, well, I could have an array. Each of the nodes, the employee nodes, could have an array of pointers. But then we're at that same problem where we don't know how many maximum people reporting would be. So if there's a maximum number of edges that any node would have, well, that's just fine. Then we could make an array. Well, the general way to make a tree is to have the nodes, instead of having an array of the pointers of their children, what you could do is you could have something like, you've got your maybe your pointer to the parent, and then you've got your payload, maybe the CEO, his name, his salary, and things like that. And then what you can do for the children, so this is going to be the children, you could have that be a linked list of nodes. And so all the children would end up going into a linked list. Now there's more overhead with doing this because you actually have to have a linked list of employee objects. But if you have a linked list, that can keep growing and growing without an arbitrary bound. So this would be the employee object, employee link object or employee node object, which would have all the relative information. It may have a parent pointer, so it knows who its parent is. And then with the children could be stored in an array if you have a fixed maximum, or they could be in the linked list. Now, the problem with having an array, as an aside here, is that if you have your array 30 nodes long, and you usually only use 2 or 3 in any given relationship, well, then you're going to have the overhead of 30 different pointers for everyone, whether they're used or not. So the linked list method has the benefit of being able to expand, but it also has the benefit of only using up as much memory as it needs to for the number of valid elements in the linked list. So this would be a way of expressing a node, and then the node has to know about its children. It also has to have its own information, and it may or may not have a link to the parent, depending on how it's set up. The only reason I'm hedging my bets on this is that we will be using a tree system that doesn't have parent nodes. There's a benefit and a drawback because it's harder to stitch things around if you have to manage this parent pointer, and technically you don't need it. Okay, so those are some examples of trees, and then this would be what we would need in order to store the information for a particular node.